Thank you. So, okay. So, Adam explained you all the theoretical aspects of information theory. So, I'm gonna talk about the application of information theory. So, we wanted to make this talk a little bit more interesting. That's why we changed the speakers, and also we dress differently. I see I could excite you very easily with this, but anyway, let's see what's the application of information theory. So there are basically three different methods to calculate information theory, which is direct method that actually gives you the correct information measure, and the two other method that gives you the boundaries that the real information, mutual information, actually lies somewhere between these two boundaries. And each of these methods has pros and cons. So I'm going to go through them one by one and explain how actually you can make this calculation. So the direct method, as Adam showed you before, is basically is calculated by this equation. So you need to calculate the entropy of the response and the conditional entropy. So for calculating the entropy of the response, you need to have a quite rich stimulus set, and you show to the neuron, and then you record the responses out of the neuron. So you can forward this distribution, and then if you repeat one specific stimulus several times, and then you record the responses, then you can form this, you can calculate the entropy, conditional entropy, actually R given S. So, but exactly how it works, so for example, Fred, for example, if you want to use direct method to calculate the information, right? So you have, I remember that you have different shapes that you're showing to before neurons, right? So you show one of these shapes for several times, like 10 times, to the neuron, and then you record the responses out of the neuron. So you can actually plot the distribution of responses. So here is the responses, and you can say how many times like firing rate 20 came out and how many times 15, and then you have PRS that you can calculate the R given S. So for that specific stimulus. So I remember how many stimuli do you have? 8. Okay, so you can, so for example, here are 3, but you can do it for like 8 different stimuli that you have the same procedure, and then you can form all these distributions here, and then you can calculate the entropy, actually a conditional entropy R given S. So when you have, the only thing that you need to do is the entropy of the response that you should calculate, and then the subtraction of this from HR will give you the mutual information. Okay, so the advantage of this method over the two other methods that I'm going to tell you later is this method gives you the actual value, but those two other methods is just boundaries, so it doesn't tell you exactly how much information is there like between the stimulus and the response. But then there are two disadvantages for this method. First of all, you need a very rich set of stimulus actually, and you need like a lot of stimuli, and then you have to repeat like at least something about 7 or even more trials for each of these stimuli. So that means that you need a lot of trials. And for you who are recording from behaving monkeys, you know that it's really difficult to keep recording from a neuron for a long period of time. So sometimes people have difficulties even just recording from one single signal and not losing them even for some minutes. So suppose that you have to run, for example, like 200 trials just to get an estimate of this IRS. So this is a disadvantage of this one. And then the other problem is that this method, it just gives you one number, which is just basically mutual information between R and S. And it doesn't tell you that what are the components of the stimulus which are preferred by that neuron. But the other two methods that I'm going to tell you later, they do this. Okay, so the other method is upper bound method. So again, as it's you can see from the name, so it gives you the upper bound that the actual information lies somewhere below this this value. So I just go back to the model that Adam showed you before. So we have actually the responses is defined by the deterministic part encoding process and the stochastic noise. So that means that, for example, when we show the same stimulus a number of times to one neuron, and then we record each time responses which are due to the presentation of one same actually stimulus, you can get different responses out of the neuron. That is just because of the noise. So if the noise is additive, when you make an average of these responses together, it gives the average. Then we expect that we can average out the noise. So it actually, this corresponds to the T here, which is produced by the deterministic process on stimulus. Okay, so then if you want to calculate the information, the thing that we have to do, we have to calculate the signal to noise ratio. But how it is possible, it's just basically you subtract this average response from each of these responses, and it gives you the noise for each trial. You calculate, so you actually present this noise from time domain into frequency domain, that is actually the power of the noise, and then you make an average of the noise, which gives you average noise power. So here you have the noise, average noise, and here you have the average response, and then by this is actually your signal, and this is your noise. So if you plot this one, you can calculate the signal to noise ratio. And then by the formula that Adam showed you before, you can calculate the information between actually T and R. So this information, as I told you before, is upper bound. So that means that the actual information is lies somewhere below this point. And this is actually, it's showing by this inequality that the information that you calculate in this way is always bigger, or the best scenario is equal to the actual information that you want to calculate. But so if this method, it's not precise, what is the reason to use that? The reason is that it requires less number of trials. With having just few trials, because this method is actually using some assumptions, where the most important is that the stimulus should have Gaussian distribution, is calculating the information between T and R, but you need less trials. Okay, so then the next method is lower bound method, which is actually all the two methods, lower bound and upper bound method. Both of them rely on the data processing inequality, which informally actually says that within a channel of information, the information could be lost but never generated. So it means that when you process an information, so at the end of the channel, the information cannot be created. You can have a loss of information from S to R and from R to S because you are processing the data. So then that means that if you calculate the mutual information between S and R, this information is bigger than when you calculate from S to S estimate, which is actually you're doing another process on this data, which is going actually, it can be any process, but here I will show you how this reverse reconstruction helps. So that's why actually, so this in lower bound method, the mutual information that we calculate is actually, it's between the S and S estimate. And what is S estimate? Is basically when you go from the spikes to the stimulus using any kind of model. It could be nonlinear or linear model. It gives you the estimate of the stimulus, and then when you calculate the mutual information between this and this, it gives you the lower bound method, which is always smaller than the real, the actual mutual information. And this is just basically, this is the diagram showing how it's possible. So just talking about the reconstruction method, yeah. Well, you know the stimulus, right? You know the stimulus, you have the stimulus, and you have the responses, okay? So then you make your model, the best model that takes you from spikes to the stimulus. Okay, so that means that you just want to do the reverse. So then you have your model. Okay, so it means that with your model actually you do another process on your data, which is actually on your spikes. Okay, so then you calculate the mutual information between the real stimulus and the stimulus that you calculated based on your model, and then you see how much information is there. And this is always smaller than the actual information or equal. The model, yeah, and this I'm going to go through that because this is one of the, okay. So this is, for example, a velocity. It's a motion stimulus showing to a fly and recording from a visual neuron, and these are the spikes coming out of the neuron. So then you can use any kind of model. It can be optimal linear filter. You can estimate here, and then you convolve with the spikes. It gives you the estimated stimulus, which is this black line, which is close to the red line, which is the actual stimulus, and then again, using the same technique of signal to noise ratio that I showed you before, you can calculate the mutual information. So, but basically, the first option for you is usually using optimal linear model. So when you use optimal linear model, for example, you can have so then, and also you have upper bound and lower bound using optimal linear model. The first thing is that by these two curves, first of all, it gives you some information about the actual information, the actual mutual information. That means that the actual information should be somewhere between these two lines. But the other use of information theory is that the difference between the upper bound and lower bound, it tells you about the nonlinearity of the system. So if you want to know how much nonlinearity you have in your system, you can just measure it by this difference. And also, the other thing which is really helpful, it tells you exactly how good is your model when you take into account some kind of nonlinearity. So suppose that this is my nonlinear model, the lower bound using nonlinear model, and then I want to use using linear model, and then I want to take into account some nonlinearities. If after using the nonlinear model, the lower bound method goes a lot up and close to the upper bound method, that means that nonlinearity is working. But if it just stays there, it means that it doesn't work. So this is another, which I think one of the most interesting part is this one. It really helps. I didn't understand what exactly. Well, the upper band, the only assumption is just the stimulus should have a Gaussian distribution. So there is no model in that. Yeah, the upper bound takes into account just the noise of the system. So there is no deterministic model or tuning curve involved, right? But then this model takes into account noise and also deterministic part. So, for example, if your system is totally linear, and then there is a noise, so what you expect is that the lower bound actually is equal to the actual value of information theory. This is what you can understand from that, and also you can also get some information about the distribution of the stimulus. When this distribution is Gaussian, then these two will be the black line and the red line, which is upper bound and the actual, will be on top of each other. So you can learn a lot about the model and your system from information theory, comparing lower bound and upper bound. Okay, so I'm going to give you some example, just one example of a real example recording from empty cells in macaque visual system. So I think all of you are quite familiar with this, with empty neurons, so I don't go over that. So empty neurons are just responsible for, involved in motion processing. And so you know that they have a tuning curve for different for directions. So it means that there is a preferred direction that they respond maximally, and then as you deviate from that angle, the response drops. So as you can see, this is a polar plot. For example, this is 45 degree to 45 degree. The maximum firing rate, which is actually firing rate, is indicated by the distance from the center. And then it goes to, like, for example, 180. It's, I believe it's the minimum response. Okay, so then these are firing rates. So what about the precision of the code? Like, how much information is in any of these directions? So when you calculate the mutual information using, for example, the direct method that I show you, you see that the tuning, the polar plot is quite different from what you see here. So what we know traditionally as preferred direction, which is basically the neuron is responding maximally to that direction, and that direction is really important because the neuron is firing the most. It's almost not just one direction here. So if you just compare the amount of information in different directions, you see this direction, and this direction, they have the same amount of information. So maybe for the downstream area, which is reading these signals from empty neurons just to decide what is exactly the stimulus, these directions, they have the same importance. So this is one interesting thing that we can learn by looking at the mutual information. The other thing is actually the choice of stimulus set. So again, this formula. So we have entropy of the response minus the conditional entropy. So depends on what is your stimulus set, what is the ensemble of the stimuli that you're using. You can have different amount of information, the different mutual information value. The reason is that when, for example, you have a very rich stimulus set, so that stimulus set evokes a wide range of responses, right? When you have a wide range of responses, this term is bigger. And also depends that what is like the temporal dynamic of the stimuli that you're using, this entropy can be bigger or smaller. So then that just tells us something about the importance of the stimulus that we use. So many people, they believe that we should use always natural stimuli instead of the kind of conventional stimuli that we use in lab. And then the reason is that because, for example, if we use two different stimuli, the traditional constant motion that we use in the lab, and also the same one but with a little bit of difference, just this neuron, this stimulus is time varying. So it means that this stimulus, instead of just going in one direction, okay, it's the one direction, it's going back and forth in the two different directions. So there is a temporal dynamic in the stimulus. So if I calculate then the mutual information for this stimulus, this is this HR coming from this raster plot, which is showing different types of stimuli going back and forth with different temporal patterns. And this one is actually the conditional entropy, which is showing the same temporal pattern over and over. And as you can see here, this spike train, the variability is really low compared to the other one. And then when you calculate the information is 12 bit per second compared to 1.5 bit per second for the constant motion. So that means that if you use a different set of stimuli, then the result could be different. That means that this neuron is able to carry a lot more information about the stimulus, about the temporal dynamics of the stimulus, that we usually do not take into account when we use a kind of constant motion. And so this is just to comparing this information. This is for the constant, and these two are for time varying stimulus. with using reconstruction and direct method. So you see the difference is huge actually. So as we expect, always reconstruction method, the value of information is lower than direct method just because this is the lower bound. Okay, so the this table is just showing you different experiments recording from different animals like fly, salamander, crickets, I don't know, electric fish, and so on. And then you can see the amount of information that they calculated. It's quite different. And for example, you see, I think the cricket is the champion. It's like 295 bits per second. It's a huge difference between these two. And then you can see that different methods can give you a different estimate of the information. So at the end, so I don't really expect you to remember all the details that we said we actually gave you in this talk, but I think it would be nice, just as a take-home message for you, just to have these 4 points in mind. So later on, when during your research or analysis, when you face with these problems, then you can maybe go back to this talk or just using information theory to solve the problem. First, information theory can tell you about the precision of the neural code. It can tell you about 3 different points that Adam at the beginning of the talk told you. First, like what is being encoded, how it's being encoded, and also what's the precision. Then it tells you about the choice of a stimulus ensemble. For example, if you want to know which stimulus is more effective than the other stimulus, it's just enough that you record from the neuron and you calculate the information, mutual information, and see which value is higher than the other. You shouldn't rely just on firing rate. You can use mutual information just to know which stimulus actually has more information to it. Then, if you're just making a model of the neuron, using upper bound and lower bound, as I explained before, helps you to understand what is the degree of nonlinearity in the system. And when you change the model and just putting some elements of nonlinearity in the model, if it's really helping or improving the model or not. And then also the last part is that if you deal with the spike timing, so you want to know how much precision is in the timing of the spike, so you sometimes come up with this idea, just do jittering and see how jittering helps. Another alternative for this one, for this problem, will be information theory, that you can use different measures for response by changing the time window, like the bin size, and then you can see how these changes can give you different values of information. So this also can be addressed by information theory. And at the end, I want to also thank Mohsen here. He helped a lot with preparing the slides and also practice talks. And yeah, that's it.